Alright, so in this video I'm gonna be explaining another important paper with the title Rewiring with Positional Encodings for Graph Neural Networks. This paper in 2023 is very important. Several recent works use positional encoding to extend the receptive fields of graph neural networks with attention mechanism. These techniques, however, extend receptive fields to the complete graph at substantial computational cost and risking a change in the inductive biases of conventional graph neural networks or require complex architecture adjustments. As a conservative alternative, we use positional encodings to expand receptive fields to R-hop neighborhoods. More specifically, our method augments the input graph with additional node or edges and uses positional encodings as node or edge features. We thus modify graphs before inputting them to a downstream graph neural network model. Instead of modifying the model itself, this makes our method model agnostic. For example, compatible with any of the existing GNN architectures. We also provide examples of positional encodings that are lossless with a one-to-one map between the original and the modified graphs. So what is topological rewiring? We modify the input graph to generate G prime in two steps. First, we expanded the receptive field. Given a graph and a positive integer, we add edges between all nodes within R hops of each other to create G prime. If G is annotated with edge features, we assign to each edge an appropriate constant feature C sub E. Positional encodings. Given only the connectivity of a rewired graph, it may not be possible to recover the connectivity of the original graph G. In the extreme, when R is large and G is connected, G prime could become fully connected, meaning that all topology is lost, removing the center cue for graph-based learning. To combat this effect, we encode the original topology of G into G prime via positional encodings. So you see the topological rewiring from perspective of black center node. The left is original graph and the right is the rewired one. Lossless encoding. While a GNN can ignore information, it cannot reconstruct information that has been lost in constructing G prime from G. Yet there can be benefits in forgetting information. Discriminative power. Following work investigating the discriminative power of GNNs, this paper shows that expanded receptive fields together with the shortest path positional encodings are strictly more powerful than 1WL test. Now, the positional encoding of a vertex or edge can be local, meaning it incorporates information from a limited size neighborhood in G, or global, in which case adding or removing a node anywhere in G could affect all the positional encodings. Our positional encodings can bias the results of the learning procedure, effectively communicating to downstream GNN which properties of G and G prime are particularly important for learning. So for any edge, the shortest path positional encoding takes P sub E to be the integer length of the shortest path in G between the corresponding nodes of E. These embeddings are lossless because G is subgraph of G. They also are free to compute given our construction of G prime. Laplacian eigenvectors embed graph vertices into Euclidean space. They are defined by the graph Laplacian matrix, and we call the result a spectral positional embedding. And our final option for positional encoding generalizes the shortest path encoding to the powers of adjacency matrix, like the previous video So these are the options that you can use, and these are the data sets. They have compared their method with graph transformer and gated graph convolutional network and graph sage, graph attention, and they see some improvement.